first, thank you very much for the introduction and for the warm welcome here. I'm very happy to be here. And really, it's a real pleasure to present what we've been doing recently. So I come from IMS Lab, which are the same letters as Alexander Schoon's lab, but under different order. I'm sorry for that. That's the French logic. And so our lab is more dedicated to electronics, but really a broad range of electronics, from materials to automatics, I would say. So my work is related to organic electronics. And so in our group, as last year, Mamati Minabas was talking during this seminar, and also Guillaume Vance. So we are part of the same group, so we share the same equipment. So first, what is organic electronics? So organic electronics is just how to replace in electronic components the inorganic semiconductors to organic semiconductors. So the organic semiconductors are composed of either small molecules or polymers. They are conjugated molecules, either the small molecules or the polymers. The difference is mainly the way of depositing them. Most of the polymers actually are processed via wet processes like spin coating, slot die, or Dr. blading, or inkjet printing, whereas most of the small molecules, at least for the commercial devices, are processed via vacuum deposition, which is costly. And so now there are some research programs dedicated to depositing small molecules via wet deposition processes. So in organic electronics, we can divide into two parts. First, electronics, using organic field effect transistors on the right-hand side, and what is called more optoelectronics. So one of the most common applications of organic electronics is organic light-emitting diodes, OLEDs, which find applications in displays and lightings, and photovoltaic cells with the applications is energy production. So what you can see here, I mean this very, very nice display here, this very large is not an OLED, I checked. It's a LED display, and on each pixel you have subpixels, which are red, green, and blue subpixels, which is this is an inorganic LED. So maybe next time I come, there will be a new building that will come out in 1 year with a so large display in organic light-emitting diodes. It wouldn't surprise me here. So in our group, we work on, we've had very, very large activities on organic photovoltaic cells and organic and polymer light-emitting diodes. We also have now an activity on perovskite light-emitting diodes and solar cells. We also work on organic field effect transistors and photodetectors. We use both solution process techniques or vacuum deposition techniques to deposit the materials. And we also have physicists in the group, so we also have an activity on the physics of organic devices, using, for example, low temperature electro-optical measurements at low temperature, for example. So just briefly, I can show you what we have. So we have two facilities, either in our lab, directly in the building. So we have all the facility, the glow boxes and the evaporators under inert atmosphere to fabricate and characterize the devices. So we are really specialized in the architecture of the devices. We are not chemists, so we don't synthesize the molecules, we just use them, and we collaborate, of course, with chemists. And we really design and optimize the devices, and we really study the physics. And we also have another facility very close to our building, which is called the Holoprotec platform. We took part in the preparation of this platform. This is a quite large clean room, and in this clean room you can go from the chemistry to really the upscaling of the organic electronic devices. So we have 3 organic and metal evaporators with a large range of sources, XPS, UPS, directly connected via a transfer line on the vacuum, so you don't have to break the vacuum, and you can directly characterize the materials without going through air. And ALD for encapsulation, and all kinds of solution processed machines to solution process the organic semiconductors like inkjet printer, screen printer, slot die, coater. So the applications of OLED, so you all know, so it started some time ago for the first commercial product in 1997, but now you all have an OLED on your telephones. So the OLEDs, or you can also find a TV, so maybe soon we will have screens like this or displays like this so large. We can also find applications in lighting. So, of course, we have commercial applications of OLEDs, but still there are things which are missing. For example, the organic electronics is mainly designed for a large area and for cheap, flexible or transparent displays, for example, which can't be made or are difficult to make with inorganic semiconductors. And if you want to make a large screen like this or a large lighting, you need to solution process the materials to decrease the cost. So this is mainly what we're dealing here, how to make the displays or the lighting using solution process techniques. So first, how is it working? So an OLED is quite simple, actually. You have two electrodes, and in between you have several organic layers, and the thickness of these organic layers is quite thin, around 100 nanometers. So you can design them on either a rigid substrate, like a glass, or a flexible one, like a polymer, PET or PEN, for example. So how it's working? So in the simplest form, once you reach the applied potential reaches the flat band potential, you inject electrons from a cathode, which is a low work function material, and you inject holes from the anode, which is a high work function material, and the recombination between the electron and the hole give rise to light, which wavelengths corresponds to the gap of the material. And of course, this is in the simplest form. Below you can see that most of the OLEDs you have on your telephones are much more complicated. You need several layers, and each layer has its own property. For example, here the holes can be injected via material, then transported, inside the emitting layer, and then blocked by the purple layer here to prevent the holes going through the whole device and reaching the other electrodes without recombining. So this kind of structure is very easy to make via vacuum deposition, but much more complicated via solution process, because once you deposit the layers on top of each other, you have to make sure that the top layer doesn't damage or dilute the bottom layer. So this is what we are working on, actually. So I've selected a couple of examples. So first on the OLED, sorry, I made a mistake on the title. So this is part of Johan Murat's thesis. So what she tried to do is to try and improve so first the efficiency and the stability of the OLEDs via solution process. So most of the OLEDs that are being done at the moment are what we call direct OLED. Direct means that holes are injected via the bottom electrode and electrons via the top electrodes. So this kind of OLEDs are very efficient. This is the kind of OLEDs you have in your telephone displays, but they are water and oxygen sensitive. This is why they are encapsulated with glass. So what we try to do is to reverse and to make more stable OLEDs using an inverse structure, which means that the electrodes have to be injected via the bottom electrode, the transparent one actually, and the holes via the top electrode. So in the literature, you can find, it's pretty recent, but you can find some papers showing that this kind of structure are much more stable, what you can see here, than conventional OLEDs. So we've been working with this, and we've also been trying to improve the stability. So the stability is quite good, but to improve the efficiency and to get efficiencies as high as with the direct structure, with the solution process depositions. So for this, you need to work on the different layers. You have several examples here, and we also need to work on the electrode and the interfacial layers to fit the electronic levels with the injection or transport of electrons and holes, and to design an appropriate architecture. So this is, for example, what we've been doing on the electrodes. So if you want to inject electrons from the bottom electrode, which is ITO, we need to modify it, because the work function of ITO is rather low, around 5 electron volts. And so we need to modify it. So first, if you deposit zinc oxide, which is a good hole transport, so this is deposited via a solder process, you reduce the energy barrier, but not enough. So what we've been doing is depositing a polymer, which you can see here. This is PEIE. This is well known in solar cells to reduce the work function of the electrode and allowing electron injection here. So we managed to reach around, I would say, 4 electron volts, which is enough to be able to inject electrons in the LUMO of the material. And then, once you have this, the efficiencies were not so good. So we tried to work on the design of the OLED. And for example, we found out using organic field effect transistors that the holes were really, the mobilities of the holes were really very, very large compared to the mobilities of the electrons. And then we tried to find a way to really focus the electrons and the holes in the emissive layer. And for example, here, if you insert what we call TPBI, we can successfully prevent holes going throughout the whole structure and being combined in the emissive layer. So in that way, we managed to find maximum efficiencies as high as with the direct OLED, and we even increased the luminescence of the OLED compared to the direct one. So this was done in solution process up to the molybdenum oxide and the anode, which was thermally evaporated. So now let's switch to organic solar cells. So organic solar cells, we also have quite large activities on this. So we make also the devices, and we try to understand and to increase the stability of these devices. So we work with the Armor company, is a French company located in Nantes, in the northwest of France. And so they are pretty good now at making organic solar cells. There are other companies, and in particular Heliatech, which deposited in France some organic solar cells on top of the roof of a junior high school. So this is reality now. It's working, but it still has to be improved, in particular in terms of efficiency and lifetime. So what we are, so first, how is it working? So this is roughly the inverse process as an OLED. So first you have when light is coming inside in the semiconductor, you have an excited formation, which is an electron-hole pair, and providing they don't recombinate, they are separated, and then transported to the electrodes. This is quite similar to what you have in silicon solar cells. But the difference here is that we don't have a p-n junction, you have a donor and an acceptor for the electron-hole pair to be able to dissociate, because in organic materials, because of the low dielectric constant, they are strongly bound compared to silicon. And so here, this is the main difference. I mean, the electron-hole pair, you need 2 materials to dissociate the electron-hole pair. So these 2 materials are either on bilayers or in a plane, so we make bulk heterojunctions. So what we are working on in our group, we work on the different layers. So if you want to make a printable solar cell, you need to develop processes for all of the layers. So in particular, the transparent electrode. So transparent electrode is usually indium tin oxide, which is not very useful in flexible substrates. So we can replace it by metallic nanowires conducting polymers or carbon nanotubes or graphene. We also work on the electron transport layer. On the active layer, because when you make a blend on the absorbing layer, you need to control the morphology. And we also have activities on the hole transport layer via solution processed, and also on the top electrodes via different techniques. So just an example, very quick, we've been working quite a lot on the hole transport layer, because in most of the literature, this is thermally evaporated. So we, during the PhD of Frédéric Guilin, we managed to solution process some oxides, and we found out that in fact those oxides were not simply layers, but they are doping the interfaces. As you can see here on the UV visible spectrum, you can see a charge transfer band appearing at higher wavelengths. And so these solution processed materials are as efficient as what you can find with thermal evaporating. We also have an activity on transparent electrodes, quite large activities, and we've been working on carbon nanotubes. We also work at the moment on conducting polymers, but we have quite large activity on silver nanowires. The problem, ITO at the moment is used, but once we want to make a flexible device, ITO is brittle, and moreover, it's very expensive. It represents around 1/3 of the price of the whole solar cell. So the idea is to replace this ITO by silver nanowires. So we managed to make quite nice electrodes with pretty good properties. In particular, if you compare ITO on the bottom, ITO on flexible substrates, you can't anneal it at very high temperature, so the resulting sheet resistance is pretty high, 50 ohms per square, to be compared to ITO on glass, which is around 10. And so with silver nanowires, we managed to go even lower than that. So this is quite interesting. And what we call the figure of merit is rather good, and at least it is enough to be inserted in electronic devices. And in particular, what is quite good, because we are making devices on flexible substrates, is that if you compare the two graphs, if you compare the number, if you just bend the electrode, and if you change the curvature radius, you can see that ITO, you have a large increase of the sheet resistance, whereas with silver nanowires, this is not the case. So these electrodes have been inserted in organic solar cells. We haven't been doing this on OLEDs at the moment. The only problem, to be honest with you, is the roughness of these electrodes. This is a quite big problem that we have to solve. So the other activities, just to finish, we have other activities, in particular on OLEDs. So we are currently trying to work on the thermally activated delayed fluorescence OLED to increase the efficiency. And in the literature, what you can find on this topic is mainly thermal evaporated molecules. So we try to use these efficient molecules using solution processed. We also have an activity on perovskite OLEDs, on inkjet printed and on solar cells, inkjet printed solar cells, and we work a lot on the stability of these organic solar cells using different structures or different materials, and the top absorption organic solar cells. And we also have an activity on light emitting transistors, organic light emitting transistors. So I thank you very much for your attention, and I'm open to questions.